Okay, so I asked you to do the last ones in this sheet. So starting with number 4, the work function of a certain metal is 3.3 times 10 to the negative 19 joules, so that's WO. Light of wavelength 500 nanometers shines on the metal, so that's the lambda of the photon, and it wants you to find the maximum kinetic energy of the electrons emitted. So it's looking for EK max. Okay, so we have our WO, we have the energy, the wavelength of our photon, and the EK max. So from the wavelength of our photon, we can find our frequency because we know C is equal to F lambda. So rearranging and cheating a little, F is equal to C over lambda. So lambda, so 2.9979 over 5 times 10 to the negative 9 should give us 5.9958 times 10 to the 14th. This is not lambda. What am I doing? F is equal to F. And that's in hertz. Okay, so once I have that, I can now get my EK max. Because from the photoelectric effect equation, EK max is equal to HF minus WO. So EK max is equal to 6.626 times 10 to the negative 34 joule seconds. F is what we just found, 5.9958 times 10 to the 14th hertz. And then minus the WO that they gave us in the question, 3 times 10 to the negative 19 joules. EK max equals, the first term gives you 3.9728 times 10 to the negative 19 joules, and you're subtracting from that 3 times 10 to the negative 19 joules. So you get an EK max of 9.728 times 10 to the negative 20 joules. Okay, now it also asked you for it in electron volts, so you would divide by 1.602 times 10 to the negative 19 joules per electron volt. And when you do that, you get an EK max to be 0.60725 electron volts. Number 4. Number 5 says the energy required to move an electron from a certain metal. That's a fancy way of saying the work function, or the WO. The energy required to remove an electron from a certain metal. That's what WO is, okay? The work needed to remove an electron, or the work function. So in this question, it's 3.6 times 10 to the negative 19 joules. What is the longest wavelength that will cause the electrons to be emitted? It's actually asking for lambda O. Longest wavelength will be smallest frequency. So our first step is we can find the frequency, because WO is equal to HFO. So FO is equal to WO over H. So this 3.6 times 10 to the negative 19 joules divided by 6.626 times 10 to the negative 34 joule seconds. And you will get an FO of 5.433 times 10 to the 14th hertz. Once you have your FO, you can now get your lambda O, because C equals F lambda. So lambda O is equal to C over FO. So 2.9979 times 10 to the 8th meters per second, and FO 5.433 times 10 to the 14th hertz. Lambda O will equal 5.5178 times 10 to the negative 7 meters. Now, in this question, I did not ask you like what color that would be, but I could have, right? And so you could look this up on your multiple choice sheet, and if you did, you would see this is green. And I think I need to add that as part of the question. The multiple choice sheet that has the little chart on the top. It's not the it's the multiple choice sheet. It's that you need the little chart of wavelengths that I put on the top corner of that sheet. All right, number 6 says, when a metal surface is illuminated by radiation of frequency 6.4 to the 14th, so this is the frequency of the photon, 6.4 times 10 to the 14th hertz, the maximum kinetic energy of the photons emitted, EK max, is 0.424 electron volts. Calculate the work function. So part A wants WO. So we know that EK max is equal to HF minus WO. We have the F, we have the EK max. Bring the W over here, the EK max over there. WO is equal to HF minus EK max. So WO equals. Now it does not ask for the energy in electron volts, so you can find it in either one here. So 6.626 times 10 to the negative 34 joule seconds. Frequency 6.4 times 10 to the 14th hertz. And then EK max is 0.24 electron volts. Okay, so notice that one is in joules and that the other is in electron volts. So I would probably change this to joules, 1.602 times 10 to the negative 19 joules per electron volt. And when you do, first term becomes 4.24064 to the negative 19 joules, and it's minus 3.8448 times 10 to the negative 20 joules. When you subtract them, you end up with 3.85616 times 10 to the negative 19 joules. Okay, so that's part A, WO. Part B wants the threshold frequency for the metal. So knowing that WO is equal to HFO, FO is just equal to WO over H. So 3.85616 to the negative 19 joules divided by 6.626 to the negative 34 joule seconds. You end up getting an FO of 5.81974 times 10 to the 14th hertz. Part B. Part C wants to know the threshold wavelength. So C equals F lambda. So lambda, oops, it's not a lambda. Lambda equals C over F. 2.9979 times 10 to the 8th meters per second divided by the 5.81974 to the 14th hertz, and you end up getting a lambda of 5.15126 times 10 to the negative 7 meters. Again, I could have asked you what color this was. If you look it up on the chart, again, you would find out it was green, which just happens to be a coincidence. Last one, number 7. Light strikes a photoemissive surface whose threshold wavelength, so lambda O, threshold wavelength, is 580 nanometers. De Broglie wavelength of the electron, lambda E, is 1.561 nanometers. What color is the light? So first step, FO is equal to C over lambda O, 2.9979 times 10 to the 8th meters per second divided by 580 times 10 to the negative 9 meters, and you get a threshold wavelength to be 5.16879 times 10 to the 14th hertz. So from that, we can find our WO, because it's equal to HFO. So 6.626 to the negative 34 joule seconds times our 5.16879 to the 14th that we just found.